So, hello everybody, this is Dr. Ritu Singh from Basic Science Department, and today's topic of discussion is phase rule. It is from Unit 3, Lecture 2. Now, phase rule, the important thing about phase rule is only applicable to systems which are at equilibrium, and it helps us to specify the changes which are going to take place when we are going to vary the variables. So, in a equilibrium, when the variables are varied, what are the changes which are going to take place in the system? That is all dealt in phase rule. Now, in phase rule we have got three important terms. One is phase, which is given by P. The other is component, which is given by C, and third is degree of freedom, which is represented by F. So, in phase rule, these are the three definitions which are used again and again, and they will be defined. So, I am going to discuss one by one. So, phase, the first is phase. Which will be denoted by P. Now, phase is a homogeneous and physically distinct part of a system which is separated from the other part by a mechanical boundary, or it is mechanically separable from the other part of the system. So, it is a homogeneous, so I repeat again, it is a homogeneous phase. Phase is a homogeneous system which is separable from the other parts by a mechanical boundary. We have got three phases, or we have read three states of matter. One is solid, the other is liquid, and third is gas. So, how we are going to take up each state of matter in phase rule? In phase rule, normally the solid which we consider is the solid which is crystalline in nature. We are not going to consider amorphous solids. So, whenever we have to define solid phase, every solid is counted as a separate phase. So, if we are having two solids, that is, it is a two phase system. If we have three solids, it is a three phase system. So, every solid is counted as a separate phase. Now, we come to liquids. We can have two types of liquids, either the liquids are miscible or the liquids are immiscible. Now, if the liquids are miscible, then it is counted as a single phase, and if we have two liquids and they are immiscible, then the two liquids will be counted as a separate phase. So, if the liquids are miscible, then it is a one phase system, and if it is immiscible, then as many liquids, as many phases. So, this goes for liquid state. If the liquids are miscible, then it is one phase. If liquids are immiscible, then as many liquids, as many phases. Now, when we come to gases, all the gases are miscible with each other. So, if gases are present in the system, then it is always counted as a single phase. So, phases, we have three phase, solid, liquid and gas. Every solid is counted as a separate phase. Gas, if they are miscible, they are counted as one phase. If they are immiscible, then as many liquids, as many phases. If we have gases, then all gases are miscible, so it will be counted as a single phase system. For example, if we have A solid plus B solid giving C gas. So, if you are asked how many phases are there, so it is a three phase system, two solid phase and one gaseous phase. Now, if the condition is this, A is gas, B is gas and C is gas, and if you are asked number of phases, then it is a one phase system. So, this is how it is going to vary. Then we have the other term is component, which is denoted by C. It is number of independent constituents which must be specified in order to define a system completely, directly or indirectly. For example, if we have aqueous solution of NaCl. So NaCl is completely miscible in water. If we ask you how many phases are there, then the phase is 1. Why? Because NaCl is soluble in water. If we come to components, then this system is having 2 components. One is water, the other is NaCl. So this is we are determining components directly. Now indirectly, the components can be determined by an equation. So C is given by substance minus relationship, and relationship here refers to number of equations. By how many equations those substances are related. So that is a relationship. So component is always given by substance minus relationship between the substance, and relationship refers to number of equations by which those substances are related to each other. So this is component. So component is number of variable constituents which must be specified to define a system completely, directly or indirectly. Indirectly, we are going to calculate by this equation. We are going to do that after defining all the definitions. Then we have degree of freedom, which is denoted by F. Now degree of freedom is number of independent variables like temperature, pressure and composition. So temperature, pressure and composition, which must be specified in order to define a system completely. So degree of freedom denoted by F, it is number of independent variables like temperature, pressure and composition which should be specified to define a system completely. That is degree of freedom. This degree of freedom is also known as variance. Now if the degree of freedom is 0, the system is non-variant. Non-variant means everything is fixed. We are not going to define, or we need not define anything. So temperature is fixed, pressure is fixed and composition is fixed. Then we say then the degree of freedom is 0. The system is non-variant. If the degree of freedom is 1, the system is univariant. The meaning of univariant is out of the 3, temperature, pressure and composition, we have to define one thing, either temperature, either pressure or composition. By defining one, the other 2 will automatically become constant after some time when the equilibrium is attained. So if the system is, if the degree of freedom is 1, the system is univariant. If the degree of freedom is 2, the system is bivariant. Bivariant means we have to define either temperature, pressure composition or temperature, composition. The other third one will automatically become constant after some time. So and so on. If degree of freedom is 3, the system is trivariant. So degree of freedom is also known as variance. So these are the 3 definitions or important components of phase rule. So first we have phase, second is components which can be defined directly or indirectly by an equation which is substance minus relationship, and third is degree of freedom. Degree of freedom is also known as variance, and the variables which we use in phase rule are temperature, pressure and composition. Next we have phase rule. So phase rule is basically, it is how the components, degree of freedom, phase and components, they are related to each other. So F plus P is equal to C plus N. N is external force or external variables which are being used. External variables are temperature and pressure, and it is taken as 2. So the phase rule is F plus P is equal to C plus 2, and normally we write it as F is equal to C minus P plus 2. F is degree of freedom, C is component, and P is phase. So this is degree of freedom, component and phase. They are related by an equation, and this is known as phase rule. Now this has come after a derivation, but we are not going to discuss derivation as it is not included in the syllabus. So by this by this phase rule we can calculate degree of freedom of various systems. So now we are going to discuss some of the examples. The first example is, suppose we have CaCO3 solid in equilibrium with Ca calcium oxide plus carbon dioxide. If this is the system and you are asked to calculate phase, component and degree of freedom, then in this system the number of phases are 3, 2 solid phase and 1 gaseous phase plus 1 gaseous phase. Then component is given by the equation which is substance minus relationship. So how many substances are there? 1, then 2, then 3. So we have 3 substances and they are related by 1 equation. So number of component is given by 2. So degree of freedom will be given by 2 minus 3 plus 2. So accordingly we will get the degree of freedom. So this is how we are going to calculate for different systems. Suppose we take up another system which is H2O in liquid state is in equilibrium with H2O in solid state. So if we see the phases, we have 2 phases, one is solid, the other is liquid. Components, water in liquid state and water in solid state is taken as a separate components, separate substance. So to calculate component, we have 2 substances and they are related by 1 equation. So number of component is 1. So the degree of freedom is 1 minus 2 plus 2. So we get the degree of freedom like this. Now if we are having another equilibrium here which is water in vapor state. Now the phases are 3, liquid phase, solid phase and vapor phase, but the component is going to remain 1. Why? Because we have 3 substances and they are related by 2 equations. Because we have 2 equilibriums, so they are counted as separate equations. So the number of component is 1 and degree of freedom is 1 minus 3 plus 2. So degree of freedom is 0. So system is non-variant. We take up another example. For example, NH4Cl in solid state undergoes decomposition forming NH3 gas plus HCl gas, and the ratio of ammonia to HCl here is 1:1. So if this condition is applied, then the derivation or the degree of freedom is going to change slightly. So phases are going to remain same, 1 solid and 2 gases. So the number of phases are 2. The gases are always miscible, so it is counted as a single phase. Now if we come to component, now before writing component, the meaning of 1:1 means we have to write one more equation where we have to specify that concentration of NH3 is equal to concentration of HCl. So this is one equation, and second equation we are going to write. Why we are writing it? Because there is a condition which is specified where the ratio is 1:1. So in the second equation we write the concentration of NH3 is equal to concentration of HCl. Now we calculate components. So substance are 3, 1, 2 and 3. So 3 substance and they are related by 2 equations. So the number of component is 1 here. So accordingly we get degree of freedom 1 minus 2 plus 2. So the degree of freedom is 1. The system is univariant when the ratio is 1:1. So this is how we are going to calculate the degree of freedom when the ratio of the product is 1:1. Now if this ratio, second condition, if this ratio is not 1:1, suppose it is 2:1 or any other ratio except 1:1, in that condition, if the ratio is not 1:1, we cannot write the second equation. So because we are not able to write the second equation in this particular system, when the ratio is not 1:1, only one equation is there. So the degree, the phase is going to remain same, 1 solid and 2 liquid phase. The component is given by, again substance are same, but it is related by 2 equations. So the number of components will be 2 here. The degree of freedom is 2 minus 2 plus 2. So the degree of here is 2. The system is bivariant. So this is the difference when the ratio is 1:1, and apart from 1:1, whatever ratio is here, we are not going to write the second equation, but we write the second equation only when the ratio is 1:1. Now we come to another example. Carbon solid plus half oxygen gas giving carbon monoxide gas, then carbon solid plus oxygen giving carbon dioxide as gas. Now this is one system. So the 2 equations, they are telling us about only one system. Now here if we consider phases, solid phase and gaseous phase, all the gases are miscible. So we have 2 phases, one solid phase and gaseous phase. These 2 solids are same. If we talk about substance, then how many components are there? 1, 2, 3 and 4. So we have 4 substance, and 4 substance, they are related by 2 equations. So number of component will be 2. So the degree of freedom is 2 minus 2 plus 2. So the degree of freedom is 2 here. So this is another example. Then we come to next example. Here we study the system is dissociation of sulfuric acid in water. Now sulfuric acid is completely soluble in water, plus it is going to completely dissociate, but in 2 equations. So when sulfuric acid dissociates in water, we have the equations are these: HSO4 minus plus we get hydronium ion. In the second step, HSO4 minus further undergoes dissociation, forming SO4 minus plus hydronium ion. This is the equation, these are the equation for dissociation of sulfuric acid in water. Now the difference from this to the other examples which I have taken, this is the first example I am taking up where we are having cations and anions. So whenever in a system we have cations and anions, then one equation we have to write down ourselves, which is the equation of electroneutrality, which shows that the number of cations in the system are equal to number of anions in the system. That means system is electrically neutral. So these 2 equations are given because of dissociation of ions, sulfuric acid in water, and the third equation we are going to write ourselves, which is electroneutrality. Equation of electroneutrality. So electroneutrality, we are going to write straight away, write down electroneutrality. We are not going to write equation as such, but the equation of electroneutrality means the number of cations, they are equal to anions. So cations in the system are equal to anions in the system. So this is the meaning of equation of electroneutrality. So if we calculate the number of phase here, then sulfuric acid is completely soluble in water. So one number of phase is going to be 1 here. If we talk about components, then we have to define the number of substance which are present. So 1, 2, 3, 4 and 5. We have got 5 substance, and how many equations are there? We have 3 equations, 1, 2 and 3. So it is 2, and accordingly we can calculate 2 minus 1 plus 2. So this will give the number of degree of freedom. So the example, this example includes cations and anions, and whenever in equations we have cations and anions, then we have to define we have to write down one more equation, which is the equation of electroneutrality. So we can discuss one more example, and that will be the last one. Suppose we are having a saturated solution of NaCl and KCl, and it is in equilibrium with its vapor phase. In equilibrium with vapor phase. So this is the system which is given. We have taken saturated solution of NaCl and KCl because they are strong electrolytes. So because they are strong electrolytes, they are going to completely dissociate if we are going to take up normal solution. So we have taken saturated solution. Why? Because we need the sign of equilibrium. So NaCl will give Na plus and Cl minus. KCl will dissociate as K plus Cl minus. Now in the next equation, because this is the system is in equilibrium with its vapor phase, so water in liquid state is in equilibrium with water in vapor state. So these are the 3 equations. The 4th equation we are going to write ourselves. Why? Because we have got cations and anions. And what is that equation? Equation of electroneutrality. So electroneutrality, this is the 4th equation which is written. So if this is the condition, then we write 4 equations. Now number of phases, this is a solid phase, this is a solid phase. So 2 solid phases are there, then we have a liquid phase, and then we have a vapor phase. So we are having 4 phases in this system. If we have to calculate components here, then components are 1, 2, 3, then 4, then 5, 6 and 7. So we have got 7 substance, sorry I was saying components, 7 substance, and they are related by 4 equations. So it is a 3 component system, and then accordingly by applying phase rule we can calculate the degree of freedom. So this is how we are going to calculate how many phases are there in the system, how many components are there in the system, and what is the degree of freedom of the system. There is one more thing. Suppose I am having this equation, gas plus iodine gas plus 2Hi gas at 40 degree Celsius. So I am applying a condition here, the temperature is 40 degree. It is not a normal or standard temperature. Whenever such kind of constants are given in the equilibrium, then the phase rule is going to change, and here the phase rule is F minus C plus 1. Why 1? Because one of the variables is fixed, and this is known as reduced phase rule. So in this equation I have the constant is temperature, the constant is temperature, we can also have a system where pressure is constant other than 1 atmosphere, because 1 atmosphere is a normal standard temperature. So, whenever a constant is there which is other than normal temperature and pressure, then the phase rule which is applied is reduced phase rule. Everything is going to remain same, but this n, the value of n in reduced phase rule is going to be 1. Now, we have got some advantages of this phase rule. Now, the advantages of the phase rule are, it helps us to classify the equilibrium, and it helps us to specify, or it helps us to know what are the changes which are taking place when we are changing temperature, we are changing pressure, or we are changing the composition. Then phase rule is applicable to macroscopic systems, and phase rule can be applied to physical equilibriums as well as chemical systems. So, physical and chemical, both equilibriums, to both the systems we can apply phase rule. Now, we have got certain limitations of this phase rule. If we talk about limitations, it is the phase rule is only applicable to systems which are at equilibrium. The phase rule is only applicable to macroscopic systems. It is not applicable to microscopic systems. And if we are having suppose a system, then every phase in that system is going to be at a constant temperature and pressure. It does, if we are having two phases, then the two phases are present at same temperature and pressure. The temperature and pressure cannot be, we cannot vary it for different phases. So, this is one of the drawbacks. And secondly, in a system, if we take solid phase and solid phase is finely divided, then it is not a good system. Why? Because if the solid phase is finely divided, then the vapor pressure of that solid is going to vary from its normal pressure, vapor pressure. So, that cannot be considered. So, these are some of the limitations of phase rule. Then we come to phase diagram. Phase diagram is basically a graphical representation between pressure and temperature, where more than one phase can coexist. So, in a graph, we are going to define different areas as a solid phase, as a liquid phase, as a vapor phase. So, within a graph, it is a graphical representation where more than one phase can coexist. So, here today we are going to discuss one component system. And the one component system which is taken up is water system. So, if we draw the phase diagram of one component system, then this is pressure versus temperature. So, this is B, this is O, this is A, this is C, and this is A dash. Now, this is a sublimation curve. This is a fusion curve. This is vaporization. And here from O to A naught, A dash is metastable state or metastable equilibrium. And this point O is a triple point. Here water exists in solid state. So in this area BOC, here it occurs in liquid state, and at the bottom it is present as vapor state. So this is the phase diagram for one component system, which is water. Now if we see the diagram, we are having four curves, OB, OA and OC. They are stable equilibriums. OA dash is not a stable equilibrium. Then we are having three areas: solid area, liquid area, and this area is where vapors are present. Then we are having a point O, where all the graphs they meet, and that is known as a triple point, which is denoted by O. So I am going to explain one by one all of the areas and curves. So we have three areas, BOC, then BOA and COA. Now if we see the three areas, BOC is having solid phase, BOA is having vapor phase, and COA is having liquid phase. So in each area we are having only one phase. So in each area phase is 1, and because we are studying one component system, so C is also 1, and the degree of freedom, if we calculate, will come out to be 2. So it is bivariant. So in each area the system is bivariant. So this is in terms of area. We are having three areas. In each area we are having a single phase. It is a one component system. The degree of freedom comes out to be 2. Now then we take up each curve one by one. First we talk about the curve OB. OB curve, the equilibrium is present between water in solid phase and water in vapor phase. So phases are 2, component is 1, the degree of freedom will be 1. The system is univariant. OB curve is a sublimation curve. Equilibrium is between solid and vapor state. Now this point B, it is a critical point. Why it is known as critical point? Because at this point we cannot distinguish solid and vapor phase, and beyond this point water is going to exist only in solid phase. So it is the highest point at which vapor can exist. So it is a critical point. So this is the curve OB. Now we come to the curve OA. Curve OA is known as vaporization curve. The equilibrium is between water in liquid state and water in vapor state. So phases are 2, component is 1, degree of freedom is 1. The system is univariant. At this point, point A is again a critical point. At this point A, water in liquid state and water in vapor states, they are indistinguishable, and beyond this point A, the water exists only in vapor state. So it is the highest point at which water is going to exist in liquid state. So this is the second curve AOA. Next we come to the curve OC. OC curve is also known as fusion curve. The equilibrium is between water in solid state and water in liquid state. So phase is 2, component is 1, degree of freedom is 1. That is going to remain same. Now if we see the curve OC or the fusion curve, it is actually not looking like a curve. It looks like a straight line, that too tilted towards pressure axis. Now it is almost a straight line. Why? Because if we have to bring about minute changes in the melting point, then the pressure changes which we require is large. So we require large pressure changes to bring about small change in melting point. That is the reason why this line is a straight line. It appears to be a straight line. It is not appearing as a curve. Secondly, This fusion line or the OC curve is tilted towards pressure axis. Now, the meaning why it is tilted towards pressure axis is with the increase in pressure, the melting point is going to decrease. So, they are inversely related. So, this is about the curve OC. Next, we come to the triple point, which is O, and at the triple point the fusion curve, the sublimation curve and the vaporization curve, they meet each other. So, all the three equilibriums, they exist at triple point, therefore, it is known as triple point. So, water in solid state is in equilibrium with water in liquid state, and this is in equilibrium with water in vapor states. So, here the number of phases are 3. Component is 1, and when we calculate the degree of freedom, it is 0. The system here is non-variant. Here temperature is fixed and pressure is also fixed. The temperature here is 0.0098 degrees Celsius. Sometimes it is also written as 0.0099 or 0.01. So, that is same. So, the temperature is fixed and pressure is 4.58 mm of mercury. So, temperature and pressure, they are fixed because it is degree of freedom is 0. The system is non-variant at the triple point. Now, we come to the last one which is a metastable state or the curve OA dash. It is metastable. Metastable means all the three curves, they are very stable, but this curve is not stable. So, it is known as metastable. Now, if we see, this is a vaporization curve and we move here, this curve, metastable curve, is an extension of this vaporization curve. Now, on vaporization curve, the equilibrium is between liquid and vapors, but as we move beyond freezing point, this curve should have changed into solid and the equilibrium between solid and vapor phase. But what happens is, beyond the freezing point, water remains in liquid state. So, that water is not a natural water and a normal water, it is known as supercooled water. So, along this curve, metastable curve, the equilibrium is between supercooled water and water in vapor state. And water in vapor state. So, this supercooled water is water which should have frozen below the freezing point, but it is present in liquid state. So, again, because it is supercooled water and water in vapor phase, so phases are 2, component is 1 and the degree of freedom will be 1 here. But this is metastable because if we are going to disturb this supercooled water, we are going to disturb it or we add a pinch of or a piece of ice into this whole supercooled water is going to solidify or gets converted into solid phase. So, the equilibrium is going to change. This will be the state of equilibrium. So, this is one component system, which is water. Here we are having 3 areas, solid, liquid and vapor phase, where in each area the number of phase is 1, component is 1, degree of freedom is 2. If we talk about stable equilibriums, sublimation, fusion and vaporization, then we have 2 phases, 1 component, degree of freedom is 1. If we talk about triple point, then we have got 3 phases, liquid phase, vapor phase and solid phase, and the degree of freedom is 0. And then we have metastable equilibrium. In metastable equilibrium, it is not a very stable equilibrium, and water beyond its freezing point should have solidified, but it is present in liquid state, and water beyond its freezing point, when it exists in liquid state, it is known as supercooled water. So, equilibrium is between supercooled water and water in vapor state. So, this is metastable state. This is not very stable. Why? Because if we add a piece of ice or we disturb it, the whole supercooled liquid or water will undergo solidification. So this is one component system. So this is all about phase rule. In phase rule, phase is important, how we calculate phase, how we calculate component, and how we are going to calculate degree of freedom. Phase rule, under phase rule, it is applicable to only system which are at equilibrium, and it helps us to know how this things are going to change, or how the equilibrium is affected when the variables are going to vary, and the variables which are considered here are temperature, pressure and composition. So this is all in phase rule. Thank you.